Welcome to the 7th lecture for Radiochemistry 702. This lecture is on radiation reactions. We're going to talk about interactions of radiation with solutions, a little bit about dosimetry, interactions of radiation with matter. We'll relate this to radiation protection, particularly how we calculate radiation safety levels in the laboratory, and then we'll end this lecture with hot atom chemistry. Fundamentally, the effects in biological systems are all similar. Radicals are formed by the interaction of radiation with water. And here's an example of some of the radicals that can be formed. We have some ionizing radiation, reaction with water. We can get excited water, hydrogen radical, hydroxyl radical, peroxides, or superoxide radicals. These radicals drive interactions and can develop into points where detrimental effects can be seen on biological systems. So it's really the interaction of radiation with the water, since the bulk of biological systems are water, that drives the formation of these radicals that's responsible for radiation damage. Interactions of radiation with matter, as we showed in the previous slide, where the interactions are some radiation, the matter itself is water, have some pretty similar commonalities. You get dissociation of molecules, and these molecules become excited, and then these excited molecules can also become ionized. For detection, this ionization is easily measured, and that's actually the route that we use for radiation detection. In air, about 35 eV of energy is formed and dissipated for each ion pair. Other gases have different values. Those are listed here. But fundamentally, the interactions ultimately have the same sort of effect. And the formation of ions is what can be used to detect radiation by radiation detectors. And basically, if you measure the total number of ions produced, since the ionization is a function of energy, I can determine the total energy from that particle that's producing the ionization. So there are three commonalities with radiation interaction, and this overview provides these commonalities. At high enough energies, the ion is bare. So for instance, if it's an alpha particle or a proton, and energy loss is through electronic excitation and ionization of stopping material. So if something is highly ionized and it goes through matter, it'll take off electrons from that matter. At velocities comparable to the K-shell electron of the stopping material, ions begin to pick up electrons. Stopping is still electronic at this point. And then at velocities comparable to the valence electrons, elastic collisions count for energy loss, and this is nuclear stopping. There's really no sharp difference between the second point and the third point. Let's review the interactions of certain particles with matter. We'll start with neutrons. Neutrons, they're neutral. There's very little interactions with electrons. The interaction is primarily confined to nuclear effects, so we can have scattering of neutrons, both elastic and inelastic. Nuclear reactions, so N gamma, NP, etc. listed here, and another nuclear reaction being fission. And as you can imagine, particularly the nuclear reactions, the N gamma or the N fission, provide signals for those interactions and can be used as a method for detecting neutrons. If we talk about positive ions, so think of an alpha particle, those processes of energy loss are primarily through interactions with electrons. You can talk about something about a maximum velocity imparted to electrons being twice the velocity. So if you consider energy from a 6 MeV alpha to an electron, the average energy from ions to electrons is on the order of 100 to 200 electron volts. This can also lead to ionization from that electron, so we can have secondary ionization. So an alpha particle come in, impart some energy to an electron, and that electron can then impart energy to other electrons. So we get secondary ionization as a result of some of these interactions. Electronic stopping, which we've talked about already, are inelastic collisions between bound electrons and the ion. We can get an excitation of the atomic electrons from this reaction. The nuclear stopping, when the velocity of the ion is close to the valence electrons, we can get elastic collisions. So that was these cases, electronic and nuclear stopping, that we discussed on the earlier slide. And we've also discussed the influence of velocity. So when the velocity of the ion is comparable to the K shell, the ion will begin to pick up electrons. So something passing through matter will be able to pick up electrons once that particle's velocity is on the order of the K shell electron. This is going to have an influence on particles interacting with different types of matter. As we discussed, there's an influence on the particle, its velocity, and the velocity of the K shell electrons. So there's actually an influence on the particle moving through different types of matter. One of the things that we will see is that the distance that a positive ion travels in matter is actually within a pretty narrow limit. As what's shown here, if we look at this figure, it shows the number of particles at a given distance from the source. We see that number remains fairly constant, and then as you come to the part where the distance that can be reached in the material, that number rapidly drops off. And this is really driven by the fact that, particularly for positive particles, you have relatively large masses. So when an alpha particle collides with an electron, bulk of the mass is with the alpha particle. You don't get much in the way of straggling. So fluctuations along this path, along the x-axis, is minimalized. When straggling is large, this range, as you can imagine, can vary greatly. Now electrons, they're also charged particles, negatively charged. They have similar energy loss mechanisms to positive ions. Again, we already talked about the average ion pair formation is about 35 electron volts in air. Number of secondary ionization. One of the major differences, however, between an electron and the positive particles we were talking about is mass. So for the same energy, this means that electron will have a higher velocity. That'll relate to it having a lower stopping power. When an electron reaches about 150 electron volts, you get almost 6,000 ion pairs per milligram centimeter squared formed. So similar to that range figure we showed for an alpha particle, the electron will have the same thing, but once it reaches a certain energy, stopping increases dramatically. Electrons can also lose a large fraction of their energy in a single collision. And since their mass is less, we expect straggling to be much more pronounced than the example we were discussing with alpha particles. One example of some of the differences in behavior with electrons is given here for electron backscattering. We use this with microscopy to evaluate information related to the Z of the material that's under examination. A significant fraction of electrons may be reflected from scattering. And one of the things we actually evaluate is there's an increase in backscattering with the atomic number of a material. So imagine that you can determine a backscattering coefficient, and along this figure, you can figure out the Z of the material that's causing the backscatter. And coupling this with microscopy, backscattering is a method to determine composition of samples under examination. Unlike the previously described charged particle interactions, photon interactions with matter vary. They have some different properties. One of these being that photons can lose most of their energy in a few interactions or a single interaction. You also need more material for interactions than an electron, or for charged particles for that matter. And the average, similar to the other reactions, however, the average energy loss per ion pair formation is about 35 electron volts in air. Photon interactions with matter can be divided into three areas. One is the photoelectric effect. We have a pictorial examination of the photoelectric effect here, where a photon ejects electrons that are bound. Photon has a given energy, and this ejected electron has an energy that's equal to its binding energy, the photon energy minus its binding energy. So we utilize this equation right here, where this is the photon energy, the binding energy, the rest of the energy is imparted to the electron. Most of these photoelectric electrons come from the K shell, and the degree of the photoelectric effect is proportional to the Z, shown here, Z to the fifth of the absorber. So as an example, for 5% photoelectric effect, the gamma energy needed for different Z's is shown here. So for a higher photoelectric effect, one would use a lower Z. Two other effects are listed here, the Compton effect and the pair production. The Compton effect is a partial interaction, so the photon loses part of its energy to the electron. So imagine here we have an incident photon, we get an electron, and then the photon is scattered. So unlike the photoelectric effect, it's only a partial transfer of energy from the photon to the electron. The photon is scattered. There's a relationship between the energy for the photon and the electron rest energy. So we can talk about the electron rest energy, the photon energy, and that'll give us some minimum for the scattered photon energy. And it's also possible to observe a backscattering peak from this Compton effect. Compton effects are often seen in gamma detectors, where you see a large, where you'll see counts above the background that are energies below a main photopeak. A final method for photon interaction with matter is pair production. In this case, a photon converts its energy to the production of a positron and an electron. This is proportional to energy and Z. It's more common at high energy. In fact, there's a threshold. And this is often observed with a 511 keV peak, because if we produce a positron, it'll interact with another electron and form this annihilation peak. So that pair production, we see from here, we have an incident photon where a positron and an electron are produced. Now here's an evaluation of interactions of photons with different matter: aluminum, copper, lead. We have cross sections versus energy. And some of the trends that we see here, these are all from 0.1 to 10 MeV. We see that for aluminum, Compton effect is fairly dominant. For copper, the photoelectric effect is higher at the lower energies. And then for lead, the photoelectric effect dominates at the lower photon energies. The Compton effect is dominant in the middle energies, and pair production is important at high energies. The other thing I'd like to have you take notice of this figure are the cross-section data. It's plotted against cross-section in aluminum. The cross-sections go up to 6. For copper, they go up to 14. And for lead, they go up to 140. So this indicates that the interaction with lead are by far the greatest. One effect of all these interactions of radiation with matter, when it comes to radiation safety, is to try to quantify the influence of a certain radiation field on radiolysis and eventually health concerns. This is the area of dosimetry, where you try to get a relationship between a measurement in a radiation field and a chemical or biological change. there should be some sort of effect of dose on a chemical or biological change. And dosimetry is a way to try to quantify this relationship. As we discussed, when these particles interact with matter, they cause ionized molecules, secondary electrons, etc. And these in turn drive chemical or biological changes. So when we talk about absorbed dose, we talk about the energy absorbed per unit mass of any target for any kind of ionizing radiation. So when we talk about absorbed dose, we talk about units such as gray or rad. We're talking about the energy absorbed, and we're not really focusing on the ionizing particle that's depositing that energy. The gray is 1 joule per kilogram. In the United States, we use the rad, where the rad is 100 ergs per gram, and it works out that 1 gray is equal to 100 rad. So for radiation dose units, we're going to have this 2 orders of magnitude difference between, say, SI units and what we use in the United States. This absorbed dose, so a gray or a rad, is often referred to as dose, and it's treated as a point function. So it has a value at every position in an irradiated object. The important thing to remember about these terms is the relationship between the SI unit and the US unit. So in this case, a gray and a rad, the difference is 2 orders of magnitude. So 1 gray is 100 rad. The dose equivalent is basically taking this absorbed dose that we talked about and normalizing it to different types of radiation. As we saw that charged particles, electrons, and photons behave differently with matter, and this influence should be described somehow when it comes to this biological effect. The difference is really driven by this linear energy transfer, and we're going to call this dose equivalence and to try to compensate for this, where the dose equivalence will be equal to the dose d times q, and q is some dimensionless value. There's a number of reports out in which define what this value should be. It's often a function of the particle and the energy. Q can vary from 1 to 20. There's some information about what Q should actually be from NCRP report that's listed here, National Council on Radiation Protection. The data that's shown here defines the Q as a function of the type of radiation. So photons, X and gamma rays, have a quality factor of 1. So what we would see for the gray would be the unit for the sievert, the rad for the rem. Electrons and positrons are 1. Neutrons are somewhat dependent upon the energy. Protons and alpha particles vary from 1 to 20. For conservative measurements, we'll just use 20 for alpha particles. So simply put, for the work that we'll focus on, we'll use 1 for photons, 1 for electrons, and alpha particles we'll use 20 to convert from a dose to dose equivalent. So when the dose is in gray, the dose equivalent is in sievert. When dose is in rad, the dose equivalent is in rem. Again, as we mentioned before, 1 gray is 100 rad, so 1 sievert is 100 rem. The biological distribution of an isotope can also be an important consideration when one evaluates internal dosimetry. And here are some examples of distribution of certain radionuclides. For instance, thyroids is a known collecting point for iodine. Calcium in the bone will mean that divalent metal ions such as strontium and radium go to the bone. Complexes, so metal ligand complex, when it goes to the kidney, the pH, there's a pH change, there's a decrease in pH. So complexes can be released, so metal ions can be released at these lower pHs. So these will have different effects on different parts of the body. So this is all related to internal dosimetry. And there's models, again, from the National Council on Radiation Protection that have models about different radionuclides and how they behave in the body. And it's also, as we'll see when we talk about annual limits on intake, a reason that radionuclides differ from one another. Right. Here's some data on some typical radiation levels. Typical background radiation, this is an updated value, is around 6.24 millisieverts per year for typical U.S. Public. That would be 624 millirem per year, again 2 orders of magnitude. And then here's some other data for consideration. If you look at the annual background of about 6 millisieverts per year, temporary short-term dose of 1,000 millisieverts causes radiation sickness. 5,000 millisieverts, 5 sieverts, short-term dose would be an LD50 for a month. And 10,000 millisieverts, 10 sieverts, as a short-term dose would be fatal. And this is a method for determining relative intensities of different radiation doses. One can perform dose calculations knowing information related to the average particle energy and its activity. If one wants to use the dose in grays per second, this equation here transforms to a very simple equation where you get 1.6 times 10 to the minus 10 A, which is the concentration in becquerels per gram, times E, which is the average energy. This equation is for alpha and beta. For alpha, the average energy can be the energy of the decay, whereas beta, since we have a range of activities, we actually use 1/3 of the beta max as the average energy. So we can show how this would work. Imagine a calculated dose of 1.2 times 10 to the 5th becquerels of carbon-14 and 50 grams of tissue. Beta max for carbon-14 is listed here, 0.15 MeV. The average energy is 1/3 of that, so about 0.052 MeV. Plugging these values into the equation, A is equal to the activity divided by 50 grams. We have our average energy listed here. Plug this into the equation. We get a value of 20 nanogray per second. Doesn't sound like a lot. The question is, how can we compare what this value is so we get an idea of whether or not that's actually a high or low dose? Well, if we compare it to the average background, we stated that the average background is 6.24 millisieverts per year. That winds up being about 2 times 10 to the minus 10 sieverts per second, or 0.2 nanosieverts per year. So this calculated dose is 2 orders of magnitude larger than the background dose. So this 20 nanosieverts per year is 100 times background. So that's a reasonable estimation, a value that one can use to compare a calculated dose with a meaningful value. We can use a different equation for calculating dose from photons. The equation is listed here, and it contains different terms. One is air absorption coefficient, mu divided by rho, shown here. This is a coefficient that describes the absorption of photons by air, and the values listed here. And this is generally consistent from 60 keV to 2 MeV. So for most photons that would be released from radioactive isotopes, this value can be utilized. We can take our dose term here, we can rearrange it into grays per second as we did for beta and alpha particles, and we get a value that says is shown here, 3.44 times 10 to the minus 17 C, which is our activity in becquerel, times E in MeV, divided by R squared, where R is a distance in meters. And remember, we also need to normalize our gamma energy to the yield of photons. So when we take C in becquerel, unless the photon yield is 100%, we need to take that into consideration. So as an example, let's consider a case where we have 10,000 becquerel of sulfur 38 that's at 0.1 meters. We know that if we look up 95% of the there's 95% gamma yield for a 1.88 MeV photon. So we could take these values and substitute it into our equation that's shown here. So D is equal to our constant, and we multiply that by the activity. So it's 10,000 becquerel. Then we need the energy, which is 1.88 MeV, and then we add the 0.95 to represent the 95% gamma yield, and we divide that by 0.1 squared, the radius, the distance in meters, and we get a dose of 6 times 10 to the minus 10 grays per second. Once you have the dose, you should be able to use that information to evaluate some detriment due to the exposure from that dose. An example of that is provided here, where you can talk about some detriment, some sort of cancer, non-fatal cancer, genetic effects. And this is parceled out for either adult workers or the population as a whole. You can think about those as different potential sets of exposed people. You can use this to evaluate what would be the detriment from a given exposure. So for instance, what is the probability of detriment for a 2 millisievert per year for 10 years to an adult worker? If we have 2 millisieverts per year times 10 years times 5.6 times 10 to the minus 2 detriment per sievert, which is given from this value, we get this value, which is basically the increased risk of having some detriment. If we look at the maximum occupational dose for 30 years, which is 50 times 10 to the minus 3 sieverts per year, we do that for 30 years, we see that the increased probability of having some detriment is 8.4%. One of the reasons that we can only evaluate this detriment as a probability has to do with the actual biological effects due to radiation exposure. As we see here, there's a table of events that can occur over a function of time due to a biological interaction with radiation. The time components here go from very short, 10 to the minus 18 seconds, to generations. Those effects, which are associated with health, cellular processes, tissue damage, clinical effects, are extremely long-term events compared to the chemical and physical nature of the interaction of biological material with radiation. Therefore, it's very difficult to quantify. However, the theory of a linear dose effect says that any amount of radiation above background is harmful, and information on that can be seen from this website. Whether or not the linear dose effect is real and how low-level radiation affects health is not clear, but the model is this linear dose effect. Based upon allowed limits, one can start to explore the limits for given radionuclides based upon their decay and biological behavior. This information is available from this NRC website. You can go here and find out the occupational value limits for any radionuclide, including the ones that we work with. There's two data sets one needs to evaluate. The annual limits on intake is derived based upon a dose received of 0.05 sievert from a given radionuclide. The ALIs, as they're called, the annual limit on intake, is listed here. And you see that there's two different ones, an oral ingestion or an inhalation. This gives you the limits on what would be the activity in microcuries for oral ingestion, in this case for americium-241. And here's the inhalation for americium-241. And you see that the differences are extremely large. The limit on intake for inhalation is usually much lower than the oral ingestion. Another unit is the derived air concentration, the DAC, and this comes from the annual limit on intake. And it's the assumption that there's a certain radionuclide in the air, and it's based upon the ALI, so the annual limit on intake, assuming that you would be breathing this air for 2,000 hours, that would be a typical work hour, and that your exchange of air is listed here as 2 times 10 to the 4th milliliters per minute. And as you can see, your derived air concentration are extremely small values, and they're listed in microcurie per milliliter. The values are shown here, and you can go to this website and get all this information for any radionuclide. Okay, using what we've just discussed, the dose, how one could calculate dose, we actually use the ALI and the DAC basis for activities that we can use in the laboratory. The information that I'm going to discuss is also available on this web page. And we use this to correlate isotope mass, experimental method, and activity levels. In the laboratory, we have 4 radiation safety levels. Rad safety level 1, which is minimal risk. You're at a fraction of an ALI, and these are for workers who are just starting to work. We can go to rad level 2, which is at up to 1 ALI. Rad level 3, we can go well above an ALI. It's broken into airborne or non-airborne. And there's also a component that says if we're using airborne or non-airborne, we have certain requirements, such as using a fume hood or a negative pressure glove box. And then for rad level 4, the levels are even higher. Again, there's requirements on using negative pressure glove boxes above certain ALI limits, and also interactions with the authorized user. So all this data is available, and one can use it to determine the risk levels or rad safety level for the experiment one is interested in performing. Data is also shown here for radionuclides that we frequently work with, the ALI ingestion level, ALI inhalation level, and then the rad levels associated with a given activity. And the activity is listed in microcuries. And you can have rad safety 1, 2, 3, whether it's airborne or not, and rad level 4, whether it's airborne or not. And again, radionuclides are listed from americium to zirconium. All this data is available, and you could use this data to calculate the necessary radiation level that you would be working with in the laboratory. An example of that is provided here. Assume that you wanted to do a level 2 for uranium-238. This is non-airborne. This is basically 1 ALI. So if we go to the tables, we see that uranium-238, rad level 2, that's 10 microcuries as our limit. So the question would be, what would 10 microcuries, what mass of uranium is that equivalent to? Well, if we use activity equals lambda n, we find n, we can get moles, and then we can get mass. So if I take 10 microcuries, I then take 10 microcuries, I convert that to becquerel, I get my decay constant for uranium-238, I solve this equation. I see that 10 microcuries is 7.6 times 10 to the 22 atoms of uranium-238. That is 0.126 moles, and that winds up being about 30 grams of uranium-238. So this says non-airborne uranium-238. So if I had 30 grams of uranium-238 in solution, I would be at 1 alley. So I could work with this on the benchtop. What would be uranium level 3, non-airborne? If I look at the table here, I see that that is 500 microcuries. So I redo my calculation from 10 microcuries to 500 microcuries. I'm increasing that by 50 times. I need to do this in a fume hood, but now I can work with 1,500 grams of uranium. We can perform the same sort of calculation for technetium. Here's the data for technetium-99. Let's say what's the value for a level 3 technetium experiment, non-airborne. I look at my table. I see that the value is 50,000 curies. And if you look at the data, it's either going to be the limit based upon the alley or up to 50,000. So technetium hits that limit. One of the reasons that the alley limit is so high is also coupled with the biological behavior of technetium per technetate. Ingested is readily passed, which is one reason that it's used in radiopharmaceuticals. So we can see that we have a value of 50,000 microcuries. We run our calculation. We convert that to becquerel. We use the decay constant for technetium-99. We get 1.8 times 10 to the 22 atoms, so many moles, and it actually works out to be about 3 grams of technetium. So we can work with up to 3 grams of technetium in a non-airborne condition in our hoods. The final topic of this lecture is on hot atom chemistry. These are the chemical processes that occur when a nuclear reaction unfolds in an isotope. This nuclear reaction can either occur through radioactive decay or through an impinging particle. This is also called the Shillard-Chalmers process. An example of hot atom chemistry is the activation of iodine and extraction of that activated iodine from water and ethyl iodide. In this case, ethyl iodide can be irradiated in a nuclear reactor. The iodine-127, the stable isotope, remains as part of the ethyl iodide. When that iodide captures a neutron and becomes iodine-128, it separates from the ethyl iodide and can be precipitated as silver iodide. In this route, only the activated iodine is separated. And this is due to the fact that the interaction with the neutron causes a chemical reaction. So that is described here. The iodine gets extracted into an aqueous phase from this organic and then precipitated. In order for this hot atom chemistry to occur, the reaction needs to overcome bond energy. Neutrons normally don't provide sufficient recoil energy. However, from a nuclear reaction you can get gamma decay. The recoil energy from the gamma decay can be calculated here with this equation. And if we look here at the table that's taken from nuclear and radiochemistry, we get the recoil energies in electron volts imparted to nuclei by different gamma energies for different masses. And remembering that we don't need that much energy, depending upon the gamma energy, to achieve a breaking of a chemical bond, since chemical bonds are only on the order of tens of electron volts. The mechanism that occurs in hot atom chemistry is that these bonds, chemical bonds, are broken due to the reaction energy. Certain conditions need to be met. only the bonds of the produced atom must be broken. In the case that we discussed earlier with the iodine, if the bonds broke both the inactive and active iodine, the separation wouldn't be very useful. And then once the bonds are broken, they shouldn't recombine with fragments, and there should not be exchange with the target molecule. The kinetics of exchange should be slow. So again, with the example with the iodine, the produced iodine 128 should not exchange with the iodine 127 on the alcohol. And there should be a reasonable route to separate the new species. Halogens have been produced with this method, as one we described on the previous page, and these isotopes listed here have been produced. Beta reactions can also be exploited in hot atom chemistry. In this case, you're just looking at recoil, and often in recoil energy, bonds aren't broken because the energy gets distributed. However, internal conversion can potentially set the atoms into an excited state, and one can utilize this rearrangement of electrons to drive chemical reactions that can be exploited to achieve the separations. And again, looking at some recoil energies expected from various decay events are listed here. As we see, beta decay, positron decay, and fission certainly has sufficient energy to achieve separations. So as a review, this chapter we discussed the interaction of radiation with matter, gave some examples, talked about dosimetry, particularly used this dosimetry to understand how we can limit and utilize radionuclides in the laboratory, and we ended this lecture on hot atom chemistry. Certain questions that you should be able to answer is compare the derived air concentration for isotopes of plutonium and cesium, calculate the dose for a given amount of material, and understand the masses of certain isotopes that can be used in our laboratories. When you've completed the lecture, please comment on the blog and respond to the PDF quiz.